All right. Hi guys. Woo. All right. I think this should be the last talk on folding schemes, except people doing cycle fold or kilo. I don't know. That's still a lot. Yeah. Okay. That's true. Never mind. But it feels like we've been through like 6 sessions of this or something. So yeah, I think a quick recap, right? We start with Nova, which is we don't need, right? Okay. Okay. Cool. I'm gonna extend the time, but anyway. Cool. So let's recap this. So from Ayush talk. Thank you so much, Ayush. So we discussed a bit about Protostar vs Protogalaxy, right? So on high level, again, Protostar being able to like fold the spatial sound protocol, which is like generalized version, not just specific to like R1CS, Plonk, all those stuff, right? And so basically we have the things called like accumulators, and then some instant. And when you think about this like accumulator or instant stuff, just imagine of it's like the like circuit proving system. So that like, oh, this is valid, and you guys can like combine it together to become a new like accumulators 2 or something. Yeah, and then you have a new things you want to fold into, instant 2, and blah blah blah, right? This is a Protostar things. Protogalaxy is pretty much like similar. It's still doing with the SPS, it's still doing with the spatial sound protocol, so it still get all the benefit of the generalization of the Protostar itself. But the cool thing is that like, look at this. This is just the accumulation, and you fold one, right? And then it produces one, and you fold another one. On the other hand, Protogalaxies allow you to basically, this is the accumulation, but instead of folding one by one, you can literally folding like k instants into it. So yeah, so oh, this is not a good picture. So yeah, in k. So yeah, basically you can fold it all at the same time and become like, yeah, another accumulation, right? And then again, you can have another like k things to fold it in. So basically like it's more natural, and it's not just like one by one step. It's not just like always like folding one, but you can folding k into it. So this is like pretty much a higher level of Protostar and Protogalaxy. And yeah, I mean, there's still some detail on the trade-off or the prover and verifier time, but yeah, let's keep it here first, and let's look more closely on the things that I usually like give us intuition or like beta or like those stuff. So it's gonna be a bit technical, a lot technical actually. But yeah, I think I will try to just provide like intuition of how this like cryptography stuff works. With I think, yeah, like it will be helpful to read this paper and in the future paper as well. So yeah, last time when we talk about Protostar, right, we have the things called like prover and verifier. So yeah, now we are talking about things called beta. So in Protostars, you have provers, you have verifier, right? And as usual, right, yeah, the prover just send like some message, and verifier send like some like R, right? And then this thing just like keep back and forth, right? But again, these like random things can be like fiat Shamir, the message can be like polynomial commitment stuff, and yeah, as I used to say earlier, and what my talk is about, basically like instead of you verifying like L equations, let's say you want to verify fi of something equal to 0, right, where I is like 1 to L. Like instead of you like verifying this one by one, basically what Protostar do is basically you just like random linear combination. So you have like fi blah 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 equals 0, right? So this one just like pick randomly, so that like if this is 0, it means that you just prove the L equations, right? And the way Protostar make this like a lot easier is that like instead of providing like, let's say L equation of beta, they can just literally provide just like beta to square, beta third, and blah blah blah, right? So yeah, instead of just like provide like random beta, you can treat this as a random as well. But Protostar goes a bit further, right? So this will have to like the prover need to send this like n beta, right? So n, yeah. But Protostar say that like, oh no, we don't want to send just like n. That's too huge. We want to send just like 2 of root n. And where does this come from? So basically, instead of sending n, protostar just send 2 sets, right? Like the first one, I think let's see it. This is not a good handwriting. So yeah, the first one is like beta square, blah 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 to the beta to the root n, right? And then -1. Sorry, thank you. Yes. And the other one is like
no -1 here because we start from the 1. Yeah, just n square.
Just n, right? Yeah. Okay. Yeah. So basically, instead of like sending all this n, the protostar thingy just send 2 sets of root n. And basically, if you see this, like you can create like this whole n things from any combination of these two. So basically, like yeah, if you want to prove like beta square root n plus 2, you can like combine this and this together or those stuff. So this thing actually, like the protostar have this thing to send this like 2 root n things to make sure that verifier can verify this thing easily, because again it's 2 random linear combination that. But yeah, I think we will see more how this beta is different in Protogalaxy. And one of the things that is different is that, like, if you see here, like in Protostar, the beta itself is in the protocol. When I mean in the protocol, it means like in the things that you want to fold. So when you think of like things to fold, you think about like circuit, and circuit means that like it needs to like prove that the verifier accept after all this interaction, right? And beta is embedded in the things that you want to fold. On the other hand, Protogalaxy doesn't behave like that. Let's talk about beta in Protogalaxy. Yeah, sure. So basically, when you fold, right? So in traditional CK, right, you have like circuit, right? You that want to prove that something is true. Like let's say, like basically when any interaction you have prover verifier, right? And they just like talk like blah blah blah, right? And at the end of the interaction, like let's say the verifier approve that this is true or something, right? Like cool. And then when we mean folding this stuff. So instead of like manually verifying this thing and another chunk of like PV and talk thing, right? This thing folding means you just like put this together into a new thing and you just verify this, which mean this and this are correct. And when I'm saying like beta is in the protocol itself, because like the beta and square root, like 2 root n here is like beta that is sent in these things. So basically it's like it's embedded in what you're folding. It's not in the protostar folding scheme, but it's in the protocol that they want to fold. So yeah, that's the first intuition that like even though it says as beta, protostar beta and Protogalaxy beta is different. And I think that's really important. And yeah, okay, so this is protostar. And let's just leave it there first. And let's look at Protogalaxy. So yeah, Protogalaxy. So yeah, so I just want to be clear again. So again, in Protostar, right, you have like yeah, just like fold to here and become this, right? And fold to here and blah blah blah. But yeah, Protogalaxy, you just fold like K instance. So let's say beta in Protogalaxy. In Galaxy. So instead of being here, Protogalaxy actually like have folding in the instance. And when we mean instance, it means that like when you want to fold stuff together, it's already there. Like okay, so if you look at Protostar, when I mean instance, I mean stuff that like got fold together. Again, this is like at the higher level, right? Because this thing is the interaction that you're going to fold. But if you look at it as a black box, like so basically this black box is just this thing or something like that, right? And when you mean instant, you mean like here you have like this thing, you have like basically when you fold, you need to update some instance, right? And instant that is like I think this is not a good way to apply, but basically you represent this black box with some variables, and when you fold, it means you update this variable. Let's say like this is like omega 1, this is like phi 2 or something, and you like fold, you mean like you update this together to get like, let's say like like this stuff. So the intuition is that like the instant is the like is on the higher level than these things that's happening on. So when we mean we fold Protogalaxy, it means that like we have this thing, and then we fold it with like another, let's say, one, and you become like another thing, right? So yeah, all I want to say is that instead of beta inside what we are folding, they literally put it in the folding itself. Like, so basically every time you fold, you will see this beta everywhere, and it will also update beta. It will be more clear later, but yeah, it's different beta, and I think that's what the first point.
Two, right?
Yeah, sorry. It's different one, yeah. It's just like when you fold, you mean you just update the instant, and when I mean instant, it's mean the thing that represent this huge all things. Yeah. Yeah, so that's the first part, and let's talk more about why I think Ayush did a pretty good job about like why Lagrange based, right? So the intuition of why Lagrange based is basically like, again, when you folding two stuff together, like let's say why Lagrange based. When you want to fold stuff together in Protostar, like basically in Protostar, you know that the accumulator is the relaxed version, right? It means that like the verifier compute like some function, it will become error, right? Like error terms. And then this instant that you want to fold into, it will be like 0, right? Because again, this is just like R1CS and relax R1CS. The accumulation one have like error or stuff. And when you want to fold in Protostar, basically what we're doing, let's say the instant here, let me say it's like M prime and M. So if you want to prove that, because oh sorry, M is just to present this like instance stuff, like the value of instant. Yeah. So again, like the folding, the core of it is basically try to convince people that like, yeah, this previous thing is like correct, right? After you fold it into the single thing. So how can we do that? So instead of let's see. I think it's M plus accum plus signal. Okay. Yeah. So this is the gist of folding. So basically, like instead of like proving this one by one, right? You need to be able to provide these things that if this is correct, this is also correct. So why is that the case? So let's say if f is like, let's say like if fix is like x squared, right? And you do this, right? So basically you become like m plus square plus 2 xm m bar plus x squared m squared. So basically, like if you can prove that if this is really correct, right? This term should be the same as this thing. It should be e. And this term, it should be 0, right? So in this case, right, again, this is polynomial, so it depends on x, so it means you can still do things that you usually do, like polynomial commitment and request like some like opening stuff. So, but the point is that like every time you want to prove that this folding things works, you need to do this like huge thing, right? Again, this is easy because this is just the degree 2. But every time, like if you want to calculate this thing, it needs to depend on degree d, right? So here, basically, yeah, so the point of Protostar is that like every time you want to verify it, you need to compute like these huge polynomial, and you can think it will get worse. Like if it's 2 to the degree 3, this thing will have like 2 or 3 two cost term, and if it's degree d, it will have like d minus 1, which is a big, right? And that means that like if you want to fold like multiple things, because this thing, right, like it just show that it folds like 2 things, right? Because this one represents this one represents this. If you want to fold like a lot of more things, it will just like grow like really big. It's not just like, yeah, so you can get the picture. It's really bad that if you just like continue doing this. So instead of like doing folding and just like be concerned about this degree stuff, we use Lagrange, because in Lagrange you doesn't need to like just explore the folding degree. So you can just like, cool, I want to prove that, like again, if you imagine how this is gonna work, right? Because this thing present this thing, this thing present this thing, but let's say if you have like 3 things, right? You're gonna have like huge polynomial, and let's say like the first term represent like instant 1, and then some cross term which is like really big, like this stuff, and then like let's say here you have like instant 2, and then like huge term here. Like this thing's gonna be really bad, right? But again, with the Lagrange, you don't need this stuff because you can just like specify the point that like cool, at this point I want to evaluate this, everything else becomes 0 because the like Lagrange things. So yeah, I think that's the intuition of like why Lagrange is neat, so that we don't need to do like some crazy polynomial multiplication and have like really large cross term. Okay, let's actually get to the protocol to make it clear. So yeah, again, all this stuff and all the stuff, thanks to Yushigin to do this stuff, it's just the intuition for the Protogalaxy. But I think the protocol itself doesn't look really hard again but again, just it's pretty straightforward. But once the intuition is that like instead of you need to like multiply a huge polynomial and depends on that, you can just use Lagrange to point out each like valuation of instance. So yeah, let's do a Protogalaxy, right? So I will just reference from the paper and explain it so that in case you guys like read in the paper, so it's easier to see. So in folding, we are having, I will explain what it is later. So yeah, as we know, right, verifier and prover. So this basically just say that like cool, all this witness just known to the prover, but this thing known to the verifier, right? This is the public things, this is the private that only the prover know. And yeah.
What's the omega W1?
Yeah. I'm gonna explain. So basically, again, the intuition here is that instead of folding accumulation, the instant, folding instant with accumulators, we have one accumulator, right, which is the running instant, and you fold like many things together. So omegas means the witness of these accumulators, and omega 1 to omega k is the witness of each circuit things that you want to fold into. Yeah, again, it's the same for this thing that this thing is like this thing is for the running accumulator, this thing for an accumulator, and these things is for the instance. Again, like why don't we have like E is error, right? Why don't we have error here? Again, it's the circuit itself. It's not the relaxed version, so the error term is 0, right? If you remember, like R1CS, that like the original not relaxed one is always 0. And yeah, essentially, like I think what confused me at first is about like these phi things. Like what is it even? Is like I think the easy way to think of it is just like it's just the way to should I say this? It's just the way to represent the protocol itself. Like remember that pictures, right? That you have like prover, verifier, and they send like my, ri, like stuff go back and forth, and then you verify stuff. So you can just like high level conceptually just think phi as a way to represent this thing. It just like means that like this is the protocol that you want to fold. Yeah, and this one is the witness that satisfy this, make this thing satisfy. And when you mean witness that make this thing satisfy, it means that so in each instant, right? In each instant you want to fold. Yeah, maybe this is already similar, right? So this one is the condition of the accumulation, right? If you remember it, like it's like really similar to protostar, so that like you have like you verify at each I, when I is the number of equation, which is like from 1 to n. Right, and basically this one is just the random linear combination to verify this, and this is equal to E. Yeah, this is just the condition that the verifier accept the circuit, right? And the same it happens for this stuff, like this is omega because this is for the accumulators. Yeah, but for this instant, it's literally the same, but with like E is the 0 because it's not a relaxed version. And yeah, I think one of the last key part that is confused in.
So beta is selected from.
Yeah, it's the.
Random, right? It's just you construct that with that
Yeah, thank you, Harry. Yeah, so basically like our beta. Yeah, thanks, Harry. Like if you remember like beta from protostar, right? Protostar beta. Like beta has like two sets, right? Like beta 1, blah blah blah, beta to the square root n, and then beta root n plus 1, beta root n plus 2, blah blah blah, beta square n, right? But again, instead of that, beta in Galaxy is beta, and this thing I usually already covered that as well. So it's this thing, blah blah blah, beta to the 2t minus 1, where t is basically log n. So like imagine like we want beta to be, we want to know value of beta from I is 1 to n, right? But again, instead of sending that n things, Protostar, oh cool, we will send these couples and then you can map it. But instead, Protogalaxy is just like, cool, we have n, right? And if you think carefully, n or anything can be decomposed into binary. And this thing is just represent like each binary bit, so they can just like send log n's of it instead.
So is beta a random number, or if it's a random number, how to make sure that one equals to e?
Which one?
So that sum.
Oh yeah. I think we shouldn't think of beta as random anymore because it's already in with instance. So every time when you fold, you will have another random number. Like beta right now is just the thing that to present the error term. Beta is in relax R1CS or anything like it. Yeah, you shouldn't think of it as random anymore because it's already baked in this thing and it will get updated every time you fold. So it's pretty deterministic, like every time you fold stuff. So yeah.
How to get the beta from the beginning?
From the beginning, right?
Yeah, just how to figure that, how to make sure that equals to e. So that's sum.
Yeah. That's a good question.
Okay, because this accumulator, right? Accumulator.
Yeah.
So if accumulator is valid, then accumulator will satisfy this equation. The next step,
Like any beta is arbitrary, right?
Fold those new instances into the run instance to keep, so that we'll have a new beta, right? By combine old beta with a new delta, right?
Yeah. So
Generate a new beta star or beta prime, something like that.
So at first, beta is pretty much arbitrary because like the first like folding accumulator, right? It just needs to satisfy this relaxed version. So beta can be anything at first, and then when you fold, beta get updated accordingly, right? Yeah.
So I did answer the question from Harry. So this is invariant. So if we updated the accumulator, then we require that the new accumulator should also satisfy this equation. Alright, because all of stuff from this one plus this one, the accumulator.
Okay. Oh my God, there's so many moving pieces. All right. So let's one last thing before we go to actual main protocol. Is the thing called, I think Sachs kind of like gloss this because it's pretty like, I don't know why they write such a general term, but basically it's the thing like if you see it here, right, it's the beta I, which makes sense, right? But in paper you will see the things called like power I of some set like X, right? So basically what this essentially is basically from this set X, how to, let's do this. Beta 2 to the 1, beta 2 to 2, blah 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 blah. Beta 2 to like t minus 1. Yeah, let's say this. So basically like thinking about this thing is basically like given this set, how do we like combine, like do it together in order to get like this like I stuff. So in this thing, like these things is equal to this thing. So basically like instead of like writing just this thing, it's just like more generalized. So like, oh cool, given this like set, how do we like compose it to be this thing? So it's just like more generalized like version of it in the paper, but essentially it's just this thing again. like in the protocol, it will have like some things like that, like let's say when you want to add like randomness or stuff, like instead of, because like essentially how you get I, right? Because like let's say you want beta to the 6, right? The way you get this is, again, it's binary, right? So 6 is like 110, right? So the way you do that is basically just like beta 4 times like beta 2, right? So yeah, basically you got like this pair and it become that thing. So essentially like power is just to basically like how to use this thing to multiple together and get a value, which is this thing. Something like that. So essentially it's I, because any I can be decomposed into binary, and yeah, specifying that. In this protocol, it will have the more stuff in here, but essentially you just think of this set as like, they just like multiply each other to get like some value of like this, like 6 become this and this times together. Okay, and yeah, let's do protocol. Let's leave this here, but that's important. I think I won't get to the sum check part because it's gonna be a bit too long.
What? Sum check?
Yeah, I already read that. What? Yeah, I don't think so. That doesn't make sense anymore. It's gonna be too long. Cool. So again, right? Beta is no longer random because it's deterministic. So the thing start with we have the random delta, and with random delta in the field, we like create like these settings. Blah 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 blah. Oops. So yeah, this thing looks really similar, right? If you see, like this is beta and it's create like beta I, and now we have like random number, which is like the same thing. Again, that's why we want to add randomness to, like, because again this beta things is the thing that makes the like sigma beta I fi omega equal to e or 0, right? If it's the instant. So basically, like if you want to prove that every of these is 0 or e again, you need to like randomize this stuff, right? Because you cannot just like use the same thing. So yeah, this is how the randomize come. So basically we have this thing already. So we will calculate a function. So the prover will compute a polynomial so yeah, so here you have beta, that is the randomness in random linear combination to prove that it's actually satisfied. But here we just provide randomness to it, right? So what this means is basically you just push this together, so it will become like power I, and yeah, just literally plus it together, like this thing plus this thing, blah blah blah, and this thing, right? And again, like instead of like beta I, you will get some kind of like some multiplication of this, like let's say maybe like beta this time like beta square plus like this square, all those stuff. So it just adds randomness to this like linear combination so that it's still valid, right? So yeah, this is called, they call the paper like refresh the randomness, because again beta is not even randomness, right? Like it used to be randomness in the first place, but again every time you fold it, beta get updated, so it's known value. So in order to make sure that like our new, because when you fold it, you want to make sure that like this thing still verify, you just update this to be like new randomness by this thing, and the way they update is this. And yeah, again, prover just calculate these huge things, and yeah, basically they know the coefficient, right? Because at the end of the day, this is just x stuff, right? Because if, oops, sorry, this is x, just put x in as well, and this is x. So yeah, so basically like this gonna be like x polynomial of t, because there is like t term of this, right? So the maximum is like x to the t. So basically prover will send coefficient, and this thing just get back to the same thing, that like of fx to e. And the intuition about this is, it's basically like if you look at the coefficient itself, like if you look at like f0, right? What is f0? F0 is basically like this thing, which just mean that like it's equal to E, right? Like this is just like the normal things, that is the baseline for this folding that you want to. But again, like the reason that we want the other like coefficient is because yeah, we want to make sure that it not only like satisfy the E, right? But it also satisfy like all these things that should be equal to 0. Because like again, like the result of the folding should represent not only this is satisfied, but also this thing satisfy. So yeah, this thing, and yeah, it's just back to the same thing, basically verifier, challenge, like alpha, yeah, as a field element, and then yeah, it's the same thing. So basically, and then prover, and then they like compute f of the alpha from these like polynomial things that they send, right? You just compute f. Okay, cool. So what do we have now? We have randomness this. We have randomness this. There's gonna be like 3 randomness in this protocol. So sorry for that. Oh, I feel really bad. So let's compute. Let me write it down first too. Bro. Okay, I think this is gonna make sense now. So yeah, this is like what the foldings come in. So basically, like you pick like this thing, right? And after you pick this thing, you know this. You saw this thing, right? You just put like alpha into this x. So basically, your beta become like beta plus like alpha gamma, right? And this thing I just call it like B update. So basically, this one will be this thing. So this one is already randomized, right? And so basically, this is our fold instant. And this must show that like cool, if this is true, it means that like this sigma stuff is E, this sigma stuff of this thing is 0 or stuff, right? So how does it make sense here? So basically, if you see here, right, if you put, again, this is Lagrange, this is the fold instance, is equal to sigma and the power of like this new update B instance, I want to n. The core thing is here. So basically, instead of doing those like a lot of like polynomial stuff as a protostar, actually let me write it clearer. Sorry, this is really important part. If just one thing you get from this. Cool. So how does this folding things, if it's like makes sense, it will represent all the fact of that folding things, right? So if you look closely, like this is the Lagrange, which means that like if x is, it's not x is equal to 0 because you need some, yeah, it's like multiplicative group, but whatever, yeah. Just for simplicity, if x is 0, this one is 1, right? And if it's not equal to that, this one is like 0. So basically, if you look at the fact that if this x, like if g of omega 0, not omega 0, let's say of 0, again, it shouldn't be 0 because it's not multiplicative subgroup, but like basically if you put x here as the thing that makes every term here disappear and leave only that term, it's like sigma power blah 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 f, right? And it will just like live here. It must be equal to e, right? Because this is the thing that corresponds to here. And again, if you have other value than 0, maybe 1, that may represent this thing, right? This term will disappear, right? Because L0, right? It's only 0, and everything here will just become like power of like f omega 1, which this should be 0 to satisfy this thing. And it's not the same. So basically, like we can prove that like if this value behave like this, it means that like all their like previous folding stuff just like makes sense, right? Because all this just like this one thing just encapsulate everything that we fold together, even though it's k instant, and the key is basically like because of its Lagrange, we don't need to like explode like the polynomial to make sure that like cool this thing represent this, because every time like yeah, if it's 2, right, it means that like we want to show that it's like satisfied here, right? And the same thing, like this will become 0. Everything except j equal to 2 will be 0, and this one will be like omega 2, 0. Those stuff. So basically like the gist of it here is that we need to show that this huge polynomial actually behave like this. So if we show that it behave like this, it means that like the folding is correct, and we can like yeah do this stuff and we'll continue this. So how do we show that it corresponds to this, right? So again, it's really clear, like if it's like 0-ish, it will become e. If it is like 1, 2 until k, it will be equal to 0, right? Yeah, so what's left is just to show that it satisfies this property, and then we are done like folding correctly. So how do we show that? We basically, so we need to show, right? We need to show that gx, let's say equal to e when like x equal to 0 and equal to 0, right? When x is equal to like 1 blah 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 till k, right? Yeah, it's just that. Again, I hate this, but it's not really like x. Yeah, it's fine, 0. This is 0. Yeah, so how we do that, right? Again, you will really like, it's really like familiar to what you know. So basically like the proof that it is 0 when x equal to this is pretty easy. It's just to prove that this thing is some vanishing polynomial, right? When this thing is like, let's say like x minus 1, x minus 2, blah 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 blah, so like x minus k, right? So like if you prove that you know something that multiplies this and equal to this, it means that like you know that like yeah, like if it's 1, this one is 0, if it's 2, this is 0, those stuff, right? So it's just become the same thing, like you just literally need to provide thing stuff. But again, the caveat here is that you need to make sure that if it's 0, it's still equal to e, right? Because right now you don't know. But okay, so how do we do that, right? Because if it's just this thing, it just satisfies this, right? Again, this is where our favorite things called Lagrange comes in again. So we need to make sure that it's equal to 0 when this thing and e when 0, right? So the easy way, oops, sorry. Oh yeah, so basically gx is this sigma power of this new update randomness times this huge f, right? And when gx is 0, I mean, because this is Lagrange, right? So this will become 1. And this is Lagrange as well, but it's from 1 to k, so this will be all 0. Yeah, so basically what you left is like sigma power, big huge things, equal to like, and times this like f omega. Okay, sorry. Good point. It's not alpha. It's not e. It's not e. It's not e. Thank you, Harry. It's not e. It's not e. Whew. It is in fact. It is f alpha, which I think you guys forgot already. But basically f alpha, bro. F alpha is e, yeah, like if you remember, we have this like alpha randomness, which is just like happens after you update these things. So yeah, we already calculate that like f alpha things after you update this. So yeah, it's become f alpha, not e. Thank you.
But finally, if you put them together, it's the the sum should be E or
No, E is gone because E is the E is the original satisfaction of these things, right? But then again, we update the randomness. It's not beta anymore. If this thing is the power of beta, it would be E. But here we update it to be beta plus alpha, blah, blah, blah here, right? So it would be this thing instead. It's like E plus term of this term, right? Yeah, pretty much that. So yeah, so again, we just do the same thing. Like we want it to be equal to this when x equals 0, 0 when this. So we just do Lagrange, right? So when Lagrange, it means that like oh, they use kx. Where here is like so this is where the Lagrange comes in again. So this thing just make sure that like if it's 0, this thing yeah, if it's this stuff, right, this thing will disappear and it will become 0 here. But yeah, if it's 0, it's like corresponding to this. Yeah, and I think after this it's just the same thing. You need to prove that you have a knowledge of these things, and the way to do that is just again send the another randomness, the last one, the third randomness, and calculate it stuff. And yeah, fuck. Yeah, I think like again this is really lost, and I can't understand people now that like why they explain this thing and no one follow through, because it's really a lot of things. But I think the key things is that like understand that in Protogalaxy beta is in instance, and understand that they make sure all of these satisfy by using Lagrange, like using Lagrange to make sure that like when x is equal to this thing is equal to like it really represents that thing. And yeah, I think after that it's just the same thing. I think I should stop here. Sorry guys. Oh yeah, there you go. Thanks. Fuck.
You post.
Yeah, I think maybe more and maybe talk more later, but yeah. Thank you guys. Wait, you're here already? Ah.